All right, in this video, we're going to cover the concept of a binomial probability. So a binomial probability are used whenever we're performing a Bernoulli trial or Bernoulli experiment. So I'm going to quickly run through this. If you want a further in-depth explanation, go back to the geometric probability video. But we have the same three conditions. Each trial must be independent. There can only be two outcomes, success or failure. And there must be a fixed number of trials that we know beforehand. All right. Some of the notation is going to be very similar to what we did in the geometric video. We know that P represents the probability of success. Q represents the probability of failure. X this time will represent the number of successes, and N is the number of trials. That is because when it comes to calculating a binomial probability, we are trying to calculate the probability of having X successes and N trials. So with the geometric, we were trying to find the probability of the first success happening in a certain number of trials. This time, we're trying to figure out what's the probability of having X successes in N trials. All right? And so listen, I'm not going to beat the bush. There is a nasty looking formula here. So the probability of having X number of successes in N trials is given by this nasty formula. I say it's nasty because of this NX in parentheses. We'll talk about that in a second. But basically, to have, X number of successes in N trials, I'm going to need my X number of successes. So that's why we have P, the probability of X, or raised to the power X. So that's the number of successes that we need, times the number of failures, right? So imagine if I have 10 trials and I want 3 successes, that means my success rate is raised to the third power. I want 3 successes, and I need 7 failures, or 10 minus 3, 7 failures. Now, the weird part comes in with this N over X. This is read as N choose X. And this is just a way of figuring out what are the different ways that I can arrange, or the different combinations of, let's say, 3 successes within 10 trials. I can either have like the first 3 be success and the 7 be failures, or there's all kinds of different ways of doing that. So that formula, which I'm not going to go over, calculates the different ways that we can arrange, or combinations of 3 within 10. Okay. All right. Expected value, expectation. We know that that's the mean. For a binomial situation, the mean is N times P. So your number of trials times your probability of success. That gives you the expected number of successes for that experiment. And the standard deviation is the square root of N times P times Q. So you take your number of trials times your probability of success times your probability of failure, take the square root. That's how you get a standard deviation. Let's look at some examples here. All right, so similar to what we did with the geometric probability, let's look at some O-negative people, right? So people with O-negative blood are called universal donors since their blood can be given to anyone. Suppose there is a 6% chance that someone has O-negative blood. Assume that 20 people randomly line up to give blood. How many people do we expect to have O-negative blood? So what the first thing you should do is, once again, define what you mean by success. In this problem, success is that someone has O-negative blood. All right. So because of that, we know that P, the probability of success, they told us 6% of people have O-negative blood. So P is 6%. N is the number of trials. In this example, it's the number of people that are standing in line. They tell us 20 people are standing in line, so N is 20. So to calculate the expected number of people to have O-negative blood, that is the expected value. And we know that is the same thing as the mean. And as we said earlier, the mean is equal to, let's verify that, the mean is equal to N times P. So our mean is equal to N times P, which for us, that will be 20 times a 0.06. Let's go to our calculator. 20 times 0.06, and we get a 1.2. So this means that we expect, 1 or 2 people to have O-negative blood. That's what that means. okay? Be careful when you do your homework. If they ask you to round to the nearest decimal place, the answer here would be 1. Expect one person, right, to have O negative blood. All right, moving along. What is the probability that exactly 4 of the donors have O negative blood? So as we've done in previous videos, we are going to once again convert this to probability notation. What is the probability that X, remember X for binomial represents the number of successes. What's the probability that the number of successes equals 4? We need exactly 4 people to have O negative blood. Well, I'm not going to even muck around with that formula. I'm going to show you straight how to do this in the in StatCrunch. All right, so let's go over there. Once again, if you're in your homework, if you click on the Get More Help, if you don't see a link for StatCrunch, click on StatCrunch. And I need to log in. All right. So now to get to our binomial calculator, it's in the same location as the geometric calculator. We hit Stat, we go to Calculators, and Binomial. Binomial. Okay. Once again, please go back and watch that geometric video, but between standard and between standard is when we're dealing with, whether we want to equal a certain value or be less than or equal to or greater than or equal to. And then between is the option whenever you want to go in between two values. But for us, this first question, we want to go back to standard. And we need to input some values here. The calculator needs to know our n, which once again is our number of trials. Our number of trials was 20. Remember, there were 20 people that were standing in line. P is our probability of success. It's the probability that somebody has O negative blood. They told us that was 6%. So 0.06 is what that is. And then let's go back to our question. We're trying to find the probability that X equals 4. So as we've seen before, we're going to click our inequality button here, select the equals option, and change our X value here to 4. We calculate that into 3 decimal places, we get a 0.023. So that's it. Once again, the n for this with number of trials was 20. The probability of success was 6%. And it turned out that our X value was 4. Hopefully that wasn't too bad. Let's do a few more. What is the probability that no more than 6 donors have O negative blood? No more than 6. So that's going to be the probability of our number of successes being no more than 6. All right, so I got my X, I got my 6. The question is, what inequality do I put in between my X and my 6? No more than 6 means 6 or less, aka less than or equal to. I can have 6, but I can't have any more than that. That means less than or equal to. All right, same scenario. So our N is still the 20 people that are waiting in line. Our P, probability of success, is still 6%. We go to our calculator. We're still in standard mode here. N is still 20, P is still 0.06. This time X is less than or equal to 6. Okay. We calculate that and we get 0.9998. I went out 4 decimal places there just so it wasn't 100%. But anyways, that's what we had. So very, very high chance that we have no more than 6 donors with O negative blood. Which, once again, does that make sense? Because remember, we expect to have just one person to have O negative blood. So for us to have no more than 6, it's a very high possibility. All right, what is the probability that at least one donor has O negative blood? At least one. So at least one is the probability that our number of successes, X, is greater than or equal to 1. Our n is still 20. Our p is still 0.06. All we got to do is go to the calculator. We're going to change our inequality to a greater than or equal to. At least means that number or more. And at least 1, we're going to change our x value to 1. And we calculate, and we get to 3 decimal places, 0.7098. Let's round that up, make that a 0.710. All right. Okay, next one. What is the probability that we have 3 or 4 donors with O negative blood? 3 or 4 donors. So that's the probability that X is equal to 3 or 4. And there's a couple ways we can go about this. What you could do is you could find the probability that we have 3 donors and then add to it the probability that we have 4 donors. That's perfectly fine. You could do it that way. Or we can use this notation where it's saying we can use that between option. And we can say this is the probability that 3 is less than or equal to our number of successes is less than 4. This will give us the exact same answer. I'm going to use the bottom option. I'm going to show you just how that between looks. Similar to what we've seen with normal probabilities. I'm going to go to between option. My n is still 20. My p is still 0.06. My lower bound is 3. My upper bound now, though, is 4. Let's calculate that. Into 3 decimal places, we get a 0.109. All right, so I'm hoping you guys are seeing how easy it is to work with that calculator, hopefully. If you have any questions, email me. Let's see if we have one more. Yes, we have one more. Would it be likely to have 10 donors with O negative blood? Well, the answer to this, without any work, really, the answer to this is, would it be likely? No. Because remember, we expect, what was our expected value? Go way back to part A. Sorry for all the scrolling. Part A, we expect just one person to have O negative blood, right? We expected one person. Okay, well, that's a qualitative kind of a non-mathematical way of looking about this. Let's actually dig into the numbers and let me show you how to verify this kind of assumption, this kind of hunch. What we need to do is we need to calculate the z-score. Remember, the z-score is a data value minus the mean over the standard deviation. And remember, this tells us how many standard deviations away from the mean our data value is. Okay? Well, Professor Dixon, we don't have a mean or a standard deviation. We do have a mean. Remember, our formula for the mean of a binomial situation is n times p, our expected value. And remember, n is 20. P is 6%, 0.06. So that's where we got the 1.2 that we got in part A, excuse me. So that's our mean. Our standard deviation is the square root of n times p times q. And so that will be the square root of 20 times 0.06 times q. And q is always found by doing 1 minus p. So p is the remaining, the complement of whatever, or q is the complement of p, right? It's whatever's remaining out of 100%. So either do 1 minus 0.06, or you can say in your mind, oh, I know that's a 0.94. This is what our standard deviation would be. So let's get a value here. Go to my calculator. I'm going to do square root 20 times 0.06 times, and I'm going to do parentheses here, 1 minus 0.06, or you can type in a 0.94 if you're understanding what that means. And there we go. We get a 1.062 as our standard deviation. So what are we going to do here? We are going to calculate, folks, the z-score, as I said. So how do we do that? The question is, would it be likely to have 10 donors? So 10 is our data value. So our z-score will be 10 minus the expected value, the mean, which is 1.2, divided by 1.062. All right, so I'm going to do open parentheses, 10 minus 1.2, close parentheses, divided by the standard deviation of 1.062. And we get a z-score to 3 decimal places of 8.286. And so the moral of the story is this, folks. Any data value more than, let's say, 3 standard deviations away to either side, remember z-score could be positive or negative, is highly unlikely. Okay? Well, we just found out that having 10 donors is more than 8 standard deviations away from the mean. Okay? So because of that, we can now finally say it is unlikely because 10 donors is more than 8 standard deviations away from the mean. Okay? All right, so you may come across some questions like that where they're looking for an explanation. That's the explanation. Get the z-score. That'll tell you how many standard deviations you're away from the mean. All right, folks, I really hope this helps you out with understanding binomial probabilities, and I look forward to seeing you in the next video.